Assalamualaikum warahmatullahi wabarakatuh and a very good day. This video is still on a one-way ANOVA chapter, but in the last part, which is part 3, which will cover examples on performing the one-way ANOVA using both manual calculation and Microsoft Excel program. Let's have a look at one further example using the manual calculation in the next slide, before we compare the ANOVA table obtained manually with the one obtained from the Microsoft Excel program. Another example in this part 3 is on task 6.3 in the Statistics for Engineers textbook on pages 133 and 134, which aims at determining the effect of phosphorus on the output of computer monitors. The sample data are given as follows. The question is modified in this slide, where instead of testing if there is any difference in the mean output of computer monitors, we are to test if there is any effect of the phosphor types on the output of computer monitors at the level of significance alpha equal to 0.025. As we can see, the sample data also come from 3 groups or 3 levels. So the number of levels in this task question, denoted by K, is 3. The sample sizes are different at different levels. Therefore, we have unequal sample sizes case. Please note that in this example and also in the other examples in the previous parts, the data are tabulated column by column for different levels or groups. However, you can also tabulate the data by rows, such as in question 5 from exercise 6 in Statistics for Engineers textbook, page 138. Whichever way the data are tabulated, the procedure remains the same. You only need to be very careful when performing the calculation. Continue with testing procedure. You can write the hypothesis statements first before calculating the sums of squares and constructing the ANOVA table. Since in this example we want to test the effect of phosphor types on the output of computer monitors, then under H0, you have all effects alpha 1, alpha 2, and alpha 3 equal to 0, which indicates the different types of phosphor do not have any effect on the output. However, under H1, at least one type has an effect on the output of the computer monitors. Next, before writing down the decision rule, you may want to first calculate the test statistic value, which is the value of calculated F ratio, through an ANOVA table. Thus, you need to begin with calculating the sums of squares. From the data shown in the previous slide, you can find the level totals and show that y1 dot is 35, y2 dot is 12, and y3 dot is 20. The sum of these level totals is the grand total y double dot given by 67. You can also identify the level sample sizes where N1 is 6, N2 is 4, and N3 is 5. The sum of these sample sizes is the total sample size denoted by capital N given by 15. Next, you can calculate the sums of squares using the available formula. First is the total sum of squares SST given by the sum of all squared observations minus the grand total squared over the capital N, giving you a value of 37.7333. Second is the treatment sum of squares SSTRT given by the sum of level total squared divided by the corresponding level sample size minus the grand total squared over the capital N, giving you a value of 20.9. And finally, the error sum of squares SSE given by the difference between SST and SSTRT, which is 16.8333. Having calculated all the sums of squares, you can now construct the one-way ANOVA table as shown in the next slide. After calculating the sums of squares, you can now construct a one-way ANOVA table as follows, with 4 rows and 5 columns. You can begin with the source of variations in the first column. The first source of variation is from the treatment or factor indicating the between group source of variation. The second source of variation comes from the errors or within group source of variation, and the last one is from the total source of variation. The second column is for the values of sums of squares. You can write the total sum of squares as ST first, followed by the treatment sum of squares as STRT, and lastly, the balance is the errors sum of squares as SE. Please make sure that you write the sums of squares values correctly in the correct cells because the values in the other columns will depend on the sums of squares that you write in the second column. The order of the table must also be correct. The third column is for the degrees of freedom. Again, you can start with the total degrees of freedom given by capital N minus 1. Since capital N is 15, then the total degrees of freedom is 15 minus 1 equal to 14. Next is the treatment degrees of freedom given by K minus 1. Since you have 3 levels or 3 groups, then the treatment degrees of freedom is 3 minus 1, which is equal to 2. The balance must be the error degrees of freedom, which is simply 14 minus 2 equal to 12. Now the fourth column is for the mean squares, obtained by dividing the sums of squares in the second column by the corresponding degrees of freedom in the third column. Therefore, the treatment mean square MSTRT is 20.9 divided by 2, giving you a value of 10.45, whereas the mean square error is obtained by dividing 16.8333 by 12, giving you a value of MSE equal to 1.4028. Finally, in the last column, you can calculate the value of F ratio by dividing the treatment mean square MSTRT by the mean square error MSE. Therefore, the calculated F ratio is 7.4495. Please note that the MSE value can be used to estimate the unknown constant error variance. Having calculated the test statistic value, which is the value of F ratio, in the ANOVA table in the previous slide, you can now complete the solution for this task 6.3. Do not forget to write down the decision rule, where you will reject the null hypothesis H0 if the calculated F ratio is greater than the right-sided critical value at the whole alpha equal to 0.025 and the degrees of freedom 2 and 12, where 2 is the treatment degrees of freedom and 12 is the error degrees of freedom. From the statistical table booklet, page 42, you can see that the critical value is 5.10. Since the calculated F ratio is 7.4495, which is greater than the critical value, you can decide to reject the null hypothesis H0 and conclude at alpha equal to 0.025 level of significance that there is a significant effect of the phosphor types on the output of computer monitors. Now suppose you are given an extra question for task 6.3 where you are to estimate the grand mean mu, the second level effect alpha 2, and the population or error standard deviation sigma. How are you going to solve this question? I would say the estimation is rather straightforward, where the solution is given as follows. Please recall the sample information first obtained from the sample data. You may use this information to estimate the selected unknown parameters. The first estimate is the estimate of the grand mean denoted by mu hat or mu cap, given by the sample grand mean obtained by dividing the grand total y double dot by the total sample size capital N. From the sample information, the grand total y double dot is given by 67, whereas the total sample size capital N is 15. Therefore, the estimated grand mean is simply 67 divided by 15, giving you a value of 4.4667. The next estimate is the estimate of the second level effect, denoted by alpha cap 2. By definition, alpha cap 2 is the difference between the estimated second level mean, mu cap 2, and the estimated grand mean, mu cap. To find the estimated second level mean, mu cap 2, you can divide the second level total y2 dot equal to 12 by the corresponding second sample size N2 equal to 4. Therefore, the estimated level effect 2 is simply 12 over 4 minus 4.4667 that you obtained earlier, giving you a value of alpha cap 2 equal to negative 1.4667. Finally, the estimate of population or error standard deviation sigma is by taking the square root of MSE. Taking the square root of MSE obtained from the ANOVA table, you can then obtain the estimated sigma, which is 1.1844. So far, we have looked at how to construct the one-way ANOVA table and calculate the value of F ratio manually. You can also perform the one-way analysis of variance by using the Microsoft Excel program, which is the simplest available program to carry out some selected and standard statistical analysis. You can also try out other more advanced statistical softwares such as SPSS and R. However, these softwares are not covered in this course syllabus. Back to using the Excel program, you may refer to section 6.5 in Statistics for Engineers textbook, pages 134 until 136 for detailed explanation. In this slide, to solve task 6.3 using Excel, what you need to do first is to insert the data in the Excel environment. Next, click on the data in the main menu where you will see data analysis. Choose this data analysis for further steps. If you do not have data analysis in your Excel data menu, then I would suggest you to do the following steps. First, go to Home in your Excel environment. Next, choose Options, where a pop-up menu will appear. Then select Add-ins in the pop-up menu, where you will get a list of add-ins to be added in your Excel program. The one you need to add is the Analysis Tool Pack. Choose the Analysis Tool Pack and click OK. You will then find the Data Analysis button appear in your Excel data menu. Then you can proceed with the statistical analysis on the one-way ANOVA as shown in the subsequent slide. When you click the Data Analysis button in the Main Data menu, this pop-up Data Analysis menu will appear. You can see a list of statistical analysis that you can perform using the Excel program. However, in this chapter, we only focus on the one-way analysis of variance, which is the same as ANOVA single factor in Excel. So, choose this ANOVA single factor and click OK to continue further. After choosing the ANOVA single factor in the Data Analysis pop-up menu and click OK, you will get another pop-up menu on ANOVA single factor. By default, the data are grouped in columns. The level of significance alpha is set at 0.05 and the output location or the result is shown in the new worksheet ply within the same file. Since the data in task 6.3 are grouped in columns, you do not change the column and let the output option be as it is. What you need to be careful is the label in the first row and the level of significance used in task 6.3, which is not 0.05 but 0.025, so this alpha value needs to be changed. Before updating the required conditions, we need to select the input range in this cell. This can be done by putting the cursor at the selected data from the first cell and drag the cursor until all the data are included together with the group labels in the first row. When you choose the data by dragging the cursor, the input range in the pop-up menu of ANOVA single factor will instantly follow. Do not forget to tick the labels in the first row since 1, 2, and 3 in the first row are not part of the observed values Yij, but these are labels to denote phosphor types 1, 2, and 3. Furthermore, the value of alpha needs to be changed to 0.025. Now you can click OK to see the output or the result immediately. When you click OK in the ANOVA single factor pop-up menu, you will instantly get the following result or output in the new Excel worksheet ply within the same file. Let's understand the output. The summary given or the descriptive statistical summary on the group data, where the first column in the summary refers to the groups 1, 2, and 3. The second column on the count refers to the level sample sizes Ni. You can see N1 is 6, N2 is 4, and N3 is 5. The total sample size capital N is not given though, but you can always calculate on your own, where capital N is simply the sum of all Ni values, which is 15. The third column on the sum is the level total Yi dot. The grand total Y double dot can be obtained by simply adding up all these level total values, giving you a value of grand total Y double dot equal to 77. The fourth column gives you the level average values, which are the estimated level means mu cap I. So, based on the information from the summary table, you can then estimate the grand mean and the level effects. The summary table also gives you the level variances in the last column. The next table is the one-way ANOVA table. You can observe that the order of the table and also the values inside the ANOVA table in Excel are exactly the same as what we had manually. You can check the values of SST, SSTRT, and SSE are all the same. You can also observe that the total degrees of freedom capital N-1, the treatment degrees of freedom K-1, and the error degrees of freedom are also the same. The values of the mean squares are also given in the fourth column in the ANOVA table, where the MSE value can be used to estimate another population parameter, which is the error variance sigma squared. The F value here is the calculated F ratio, whereas the F crit here is the right-sided critical value F at alpha equal to 0.025 and the degrees of freedom 2 and 12 given by 5.10, which is correct to 2 decimal places, exactly the same as what we had earlier from the statistical table booklet. An extra value given by Excel is the p-value, which is the probability value that the F random variable is greater than the calculated F ratio. We will see later how to use the p-value in the alternative decision rule when performing the statistical hypothesis testing in a one-way analysis of variance. Using the Excel output, you still need to complete the testing procedure by stating the hypothesis statements H0 and H1, decision rule, decision statement, and conclusion. Now, suppose we alter back the question for task 6.3, which reads as follows. Do the data provide sufficient evidence to conclude that there is a difference in the mean output of the computer monitors due to different phosphor types at the level of significance alpha equal to 0.025? The solution starts with H0, where under H0 the means mu1, mu2, and mu3 are all equal, whereas under H1 mu I is not equal to mu j for at least one ij. The decision rule is to reject H0 if the F-test or the calculated F ratio is greater than the right-sided critical value given by 5.10. As before, you will have the same decision, that is, to reject H0 since the calculated F ratio is greater than the critical value. You can then conclude at alpha equal to 0.025 level of significance that there is a significant difference in the mean output of computer monitors due to different phosphor types. Since Excel output gives a p-value defined by the probability that a random variable f is greater than or at least equal to the calculated f ratio, you can actually use this p-value in the decision rule, where instead of comparing the test statistic value, which is the calculated F ratio, with the critical value, you can actually compare the p-value with the level of significance alpha directly in the alternative decision rule. To understand the use of p-value in the decision rule, let's recall the F distribution learned in Chapter 3, where the right-sided F-score or F-critical value at alpha and degrees of freedom nu1 and nu2 are as shown in this figure, whereas the red shaded region is the alpha level of significance defined as the probability that the random variable f is at least the critical value f alpha nu1 nu2. Suppose the calculated F ratio is located here in the critical region. The yellow shaded region then is the p-value, which is obviously smaller than the red shaded area given by alpha. Therefore, the alternative decision rule when using the p-value is to reject H0 if the p-value is smaller than the level of significance alpha, which implies that the calculated F ratio is larger than the right-sided critical value. The conclusion will be exactly the same when you use any of the decision rules. Back to task 6.3, you can use the p-value from the Excel output to make a statistical decision. Nonetheless, you still need to write down the null and alternative hypothesis statements, which are the same as before. But the way you write the decision rule is now changed, where you will reject the null hypothesis H0 if the p-value is smaller than the level of significance alpha, which is equal to 0.025 in this task 6.3. Since the p-value given by Excel is 0.007883, which is much smaller than 0.025, then the decision is to reject the null hypothesis H0. The conclusion is then exactly the same as before, where you can conclude at alpha equal to 0.025 that there is a significant difference in the mean output of computer monitors due to different phosphor types. After performing the one-way ANOVA using Excel and using the p-value in the decision rule, we are at the end of part 3, or precisely at the end of this chapter on a one-way analysis of variance. Let's look again at this chapter learning objectives. By now, you should be able to achieve all 6 learning objectives, where learning objective number 1, 2, 3, and 4 should be achieved at the end of parts 1 and 2, whereas objectives 5 and 6 should be achieved at the end of this part 3. You may want to rewatch the 3 videos to make sure you get the full grip of the fundamental concepts on this chapter and able to do the necessary calculations correctly. That's all for the one-way ANOVA. More practical questions will be given in the Chapter 6 supplementary exercise. Until then, Assalamualaikum warahmatullahi wabarakatuh, and see you again in the next last chapter on simple linear regression very soon. Bye for now and take care.